We'd like to take a look at a couple of additional examples for the disk method. Our objective is to be able to write a definite integral that gives the volume of a solid of revolution that is obtained by revolving a region in the xy plane about a specified axis of revolution. So here's the disk method, and if we have a horizontal axis of revolution, we will be integrating with respect to x, and tomorrow we will see what happens when we have a vertical axis of revolution and why in that case it would be correct to integrate with respect to y for the disk method. But our focus today is on a horizontal axis of revolution, and as we saw in our introductory lesson, this disk method is derived from the pre-calculus formula for the volume of a right circular cylinder, where we have pi r squared giving the area of the base multiplied by the height to give the volume of a right circular cylinder. And then of course we went through writing a Riemann sum and taking the limit of the Riemann sum as the norm of the partition approached 0. The Riemann sum gave us an approximation for the volume of the solid of revolution, and when we took the limit of the Riemann sum as the norm of the partition approached 0, and if the limit exists, then we get this definite integral giving us the exact volume of our solid of revolution. So in this lesson we're going to focus on a couple of problems where we would like to be able to write the definite integral that would give us the exact volume of our solid of revolution. The instructions we have are to write a definite integral to find the volume of the solid of revolution obtained by taking this region and revolving it about this axis of revolution. So our region is in quadrant 1, and it is bounded by the graphs of y is equal to negative x squared plus 5, which is shown here, and y is equal to 1, which is of course shown here. And it is in quadrant 1, so it would be this region here. We want to take that region and we want to revolve it about a particular axis of revolution. What is our axis of revolution? The line y is equal to 1. So here's our axis of revolution. In our previous example, the x-axis was our axis of revolution. In this example, it is the horizontal line y is equal to 1. So how do we go about this problem? You should begin by drawing a representative rectangle in your region. So I will begin by drawing a representative rectangle in our region. So this is our representative rectangle. And then you've got to understand that we want to take this representative rectangle and revolve it about the axis of revolution. So when we do that, what we get is a disk. We get a disk or a cylinder. So what does that look like? It looks like this. And for this disk, we can find the area of the base. The area of the circular base can be found. And the way we can find the area of the circular base is by knowing the radius of the circular base and doing pi r squared, which will give us the area of the circular base. And then from pre-calculus, we know that to find the volume of the cylinder, once you have the area of the circular base, you need to multiply by the height, which in our particular problem here will be the width of one subinterval from our partition of the interval from x is equal to 0 to x is equal to 2. So it is delta x sub I, and that is why we have integration with respect to x. And the reason why we have the disk method is because when we revolve that rectangle about the axis of revolution, we get a disk. We're actually close to being done. We've already decided that we need to use the disk method and that we will integrate with respect to x. So all we really need are two more things. What is going to be our integrand and what will be the limits of integration? Our integrand has to be a function of x because we're integrating with respect to x. And it has to give us the radius of a particular disk. So let me draw that using blue ink. Or actually, I'll just draw it using gold so that it stands out a little bit. So here's going to be a vertical line segment. And that vertical line segment is, in fact, going to give us the radius of a particular disk. And how do you find the length of this vertical line segment? You subtract the y coordinates of the top and the bottom endpoints. So the top endpoint will have coordinates x, comma, y, but it's on the graph of y is equal to negative x squared plus 5. So you'll have x, comma, negative x squared plus 5. And the bottom endpoint will have coordinates x, comma, y, but it's on the graph of y is equal to 1, so you'll have x, comma, 1. So r of x is equal to the length of that vertical line segment, which we find by subtracting the y coordinates of the top and the bottom endpoints, giving us negative x squared plus 5 minus 1. And that, of course, simplifies to 5 minus 1 is 4, so you'll have negative x squared plus 4. Which you can write, if you prefer, as 4 minus x squared. What about the limits of integration? For the limits of integration, you've got to understand that you're going to be looking at this region in the xy plane and revolving it about the horizontal line y is equal to 1 to obtain our solid of revolution. So your leftmost cylinder will start at x is equal to 0, and your rightmost cylinder will end at x is equal to 2. So the limits of integration are from x is equal to 0 to x is equal to 2. With that, I'm able to write my definite integral, and I write volume is equal to pi times the definite integral from x is equal to 0 to x is equal to 2. R of x is right here. I can either write it as I have it, or I can write 4 minus x squared. But the important thing is you have to square r of x, because you need to square the radius. So you've got to square that, and there it is. This is the definite integral that would give us the volume of our solid of revolution. We're not going to get into evaluating the definite integral, but if you wanted to evaluate it, you would have to do the following. You would have to use the fundamental theorem of calculus, but before you can do that, you need to multiply out the integrand. So you have to do FOIL here, multiply out the integrand. You'll have a function after you multiply out the integrand, and then you will use the fundamental theorem of calculus. For our second example, we'd like to write a definite integral for the volume of the solid of revolution obtained by taking the shaded region, the green shaded region, and revolving it about the axis of revolution, y is equal to 5. So a couple of observations about the shaded region. The shaded region is bounded by the graphs of y is equal to x squared minus 4 and y is equal to 5. Of course, the graph of y is equal to 5 is a horizontal line, and the graph of y is equal to x squared minus 4 is a parabola. And you will also notice that the shaded region starts at x is equal to negative 3, and it ends at x is equal to positive 3. So what is it that we want to do? We want to take this green region and revolve it about the axis of revolution to obtain a solid of revolution, and we're trying to write a definite integral for the volume of this solid of revolution. So here's the process that you need to follow for these types of problems. You need to begin by sketching a representative rectangle in your region. And then you need to visualize what happens when you revolve this rectangle about the axis of revolution. You will get a disk, and that is why you will have to use the disk method. So let's go ahead and sketch our disk here. It would look something like this. So here's our disk. And you can see that the radius for our disk is going to be the length of this vertical line segment. And I will highlight the vertical line segment in gold. So this is the vertical line segment that I'm now highlighting in gold, whose length will give us the radius of our particular disk. So we need to find a function of x that would give us the radius and then square it. And why do we integrate with respect to x? Because the height of a particular disk is going to be given by a change in x values between consecutive partition points of our interval from x is equal to -3 to x is equal to +3. So we know we should integrate with respect to x. We also know that we should use the disk method. So now all we really need is our integrand and the limits of integration. The limits of integration are going to be from x is equal to -3 to x is equal to +3, because our region starts at x is equal to -3 and it ends at x is equal to +3. So we really just need the integrand now. So we need to first find our function of x that would give us the length of that vertical line segment, which will be, of course, the radius of a particular disk. So I'm just going to erase a little bit so we can focus on what we want. So we want the length of that vertical line segment. So how do you find the length of a vertical line segment? This is the same thing that we learned a couple of days ago from our worksheet about finding the lengths of horizontal and vertical line segments. Write the coordinates of the two endpoints. The top endpoint has coordinates x, comma, 5, because the top endpoint is on the horizontal line y is equal to 5. And the bottom endpoint has coordinates x, comma, y is x squared minus 4. And the reason for that is because the bottom endpoint is on the graph of y is equal to x squared minus 4. So how do you get r? It's the length of a vertical line segment, so subtract the y coordinates of the top and the bottom endpoints to get r of x. So r of x is 5 minus, in parentheses, x squared minus 4. So you should distribute the minus sign and you would get 5 minus x squared minus -4 is plus 4. So you get 5 plus 4 is 9. So I get 9 minus x squared. So that is going to be r of x. So with that and the limits of integration that we had discussed earlier, we can write volume is equal to the definite integral from -3 to +3. R of x is 9 minus x squared, and we're going to square that because that's what we have to do for the disk method, and then we have integration with respect to x. For this particular problem, there is symmetry, and if you want to take advantage of the symmetry, you can integrate instead of from -3 to 3, from 0 to 3, and that would give you the volume of half of our solid of revolution. So you would then take that volume and you would multiply by 2 to get the volume of the full solid of revolution. So we looked at a couple of additional examples for using the disk method with the horizontal axis of revolution, and we focused on being able to write definite integrals that gave us volumes of solids of revolution obtained by revolving a region in the xy plane about a specified axis of revolution.